Okay, you guys, let's go ahead and start today's lesson. All right, so hopefully you guys be able to pick up these two that we have over here. So let's go over to the first activity that we have today. So you guys will have to go over to your this little link right here. So have your Chromebooks out and get a new tab. Type in this tinyurl.com/regressions applet. Okay. As you're done pulling that up, this is where you should be seeing, right? So over here, I'm going to go ahead and create a least square regression line out of 10 points. Okay, and the way you want to do this is you go to your little page here. You're going to add 10 points in here. So let's just click on somewhere over here. And remember, least square regression, you want to add the points that just look like a line, right? So these points. All right. So line here. So I have 10 of them. My correlation here is 0.9764. I'm going to go ahead and select show the least square line, which is right here. This is the line that was created from all these points, right? Calculating from the distance from all these points and get the best fit line. Okay, since our point almost already creating a line here. So you were to click on show residual here, which is the distance from each of the point to this line. It's going to look very tiny, okay? Very small. Okay? The smaller the residual, the better your least square regression line is going to be, because it's telling you that it's this linear equation would best describe these points. Okay. We're going to also be able to look at the correlation coefficient here. Again, correlation coefficient will tell you how good is your line, right? Again, small residual, which means that your correlation coefficient will be very high. Right? The closer it is to 1, the better your line will be, okay? So let's go ahead and perform this activity here. So we have over here, we said predict if the slope, the y-intercept, and the correlation will increase, decrease, or stay about the same. Part A saying you want to add point A. So this illustration right here, point A look like it is a point that is laying below your line, but it's look like a horizontal, right? Just horizontally comparing to all your point here, but it's going to be below your line. So if I were to add that point, then what will happen to the slope, the y-intercept, and the correlation? So let's go here and put a point. Okay, so all my points over here. I'm going to add a point right here. So what happened here? So you see that this point have a very big residual, right? Now, if I were to add this point and I'm trying to make the line or trying to create a least square regression line here, then all of a sudden, my residual for all of the other point will also increase, right? And if it's increased, that means your correlation will decrease. This is telling you that, hey, adding this point here or having this point in your least square regression line or your data will make your data not really so linear anymore, because all of a sudden you have your line look like it's all your point at first was creating all this looking line, right? And now this have to be accounting for this one extra point right here. That doesn't make your point look like a line anymore, right? So this is what was something called, we call an outlier, a point that is influence all the other points. It's also influence your least square regression line, right? So if we were to look at this, if I were to click this again, I'd be able to go back to remove that point. But by adding that, I'm seeing that, okay, my line is tilting less, right? It was tilting a lot earlier. But if I were to add a point here, it's tilting less. In a way, imagine it like a scale, and you were to add something that is very heavy on to the right, right? Now the scale is tilting less. Now, what happened to your y-intercept here? So if I remove this, your y-intercept is all the way down here. If I were to add the point there, your y-intercept is going way up. So it's increased, right? Now, earlier I said the tiltiness, which is your slope, it tilt less. So which means your slope is decreasing, agree? And then we also talk about what here? Your correlation again. My correlation earlier was 0.9764. Very good correlation here. Very close to 1, right? If I were to add a point here, it's going down to what? 0.4810, right? My correlation decrease is telling me that, hey, my least square regression line is not so good, all right? I can't really use this line to predict the future because of this one point right here that messed up the entire thing, right? My data might not follow linear anymore if I were to keep this point in the data point, right? If I were to remove it, then yes, all my data forming a line, but if I put it right there, not so much because it's go line and all of a sudden it's go down, right? If I were to try to draw a line, this line is not really good to approximate all your data here, right? Because of these large residuals of this one point. Okay. So that is something we call an outlier, right? That's an outlier. So you can either delete that point so that you can use this line right here, this model, or you have to do some kind of transformation, which we're gonna touch base later. So let's go over here and write what we observe. So the slope is tilt less, right? So the slope will decrease here. The y-intercept increase actually. That's what we saw. And the correlation will also decrease here. Rose, little, there, decrease. Okay. So that's happened if you want to add point A, a point that is way below your, or way further away from all your point, but it's below the line. What happened if you were to add point B? So above the line, or still away from all your point. So if I were to add a point right here, again, same thing, your line tilt less, your y-intercept increase, and then your correlation will also decrease here, right? So same thing here, your slope decrease, your y increase, and your correlation will decrease. Okay. Now point A and B will tilt the line. Okay. I'm calling A and B, or point A and B. These two, I'm calling them horizontal outlier. Okay, they have outlier because they have very large residual. They are further away from the rest of your data and distance themselves from the line, right? They got big influence to your line here. It tilt your line by a lot, and it decrease your correlation coefficient by a lot too. So horizontal outlier, okay, because they laying horizontally, right? Horizontally. All right. Now the next one we want to look at is to add in point C. So let's say you have a point that is look like it's vertical to all your data point, right? It's laying vertical to all your data points. Still, it have big outlier, right? I'm sorry, it has a big residual because again, the distance from these points C and D will still further away from your line, right? But it's still going to be laying vertically the same where your data is at, right? So if I were to look over here, I'm going to add a point just right below this point. Click on that. Okay. It's looked like your correlation decreased a little bit. Your slope doesn't look like it's changed or tilting. Like the tiltiness still look like it's the same. Now your Y, however, do you see it's decreasing? So it was up here. So we're to add a point now, right down here. It's looked like the tilt is the same. Your correlation decrease, and then also your Y intercept, right? If you were to put a point below your line, which makes sense, right? It's just going to shift your line. So let's go back to here and write what we observed here. The slope pretty much stay the same because the tiltiness is still the same. Your Y-intercept will decrease. That's what we saw. And your correlation will also decrease. Okay. So that's when we at point C. What about when we're at point D? A point is above your line, but still it's going to be near all your data. So let's go back to here. Let's remove that point we just at here and put a point right above all these points. Put it right here. Okay. Again, if you take a look at that, you can see that all your line, your tiltiness will still be the same. However, your correlation, yes, is going down, right? And also your Y here is went up, isn't it? So I remove that, I click on that, move, click, you can see how it's the same tiltiness. Your Y intercept go up, but your correlation will still be going down, right? Because it will still add a very big residual here. This was still an outlier. It's far away from all your point, from this line, really. That's why your correlation will go down, because we're adding outlier, right? So your slope here, still same slope. However, your Y-intercept will increase now. But since we're adding outlier, your correlation, basically telling you how good is your line, right? Will also decrease because of your residual will increase. The error, right? How far away your data is. So what we have over here, point C and D, I'm calling them the vertical outlier. Okay, these are vertical outlier. And when you have vertical outlier, what it does is going to shift the line up or down. Okay, that's all it does, because your slope will stay the same, still impact your correlation, but your Y-intercept will just go up or down, right? The line will just go shift up and down. So for number 3, let's answer that. Why are point A, B, C, and D considered outlier? Again, they are considered outlier because of their huge residual, right? They're distant to the line, right? If you were to look at this illustration here, you can see that the distance from B to the line, A to the line, C to the line, and D to the line, they are all longer than the rest of the data, right? The rest of your data, these are very small one. This one, not so much, right? You can see that. So down here, we can say that they don't follow the overall linear trend, right? It doesn't follow the same trend like all the rest of the point, right? The rest of the point was following the trend that is creating a line. These guys were outlier that is very far away from your line, so their residual is extremely big. So that's why it doesn't follow the trend of a line, right? Of your linear equation. Basically, it's telling you that they have large residual. Okay. Number 4, which outlier have the greatest impact on your least square regression line, vertical or horizontal? Now remember earlier when I have horizontal outlier, which is my A and B, you see how my correlation went down real big, right? It was 0.9 something, it went down to 0.4 something. Okay, really depending on if you were to put A or B, but still, it went down by a lot. Not so much for the vertical, right? The vertical did went down a little bit, but not so much. So the one that got the biggest impact will be your horizontal outlier. So we can say right here, horizontal outlier, because they are called the high leverage point. Okay, they have very large residuals, but removing them will positively improve your regression line, right? Now we also have influential point. We call something an influential point. Something is an influential point is when if you remove, it will substantially change the slope, the y-intercept, and or your correlation. Okay. So those are influential point, right? Your outlier here, these point. Okay. Let's go over here and do a quick notes here, recap. So what did we just learn? We learned about outliers and how they impact your least square regression line, right? So outlier are a point that is out of the parent. That is, they have large residual. Mm-hmm. Your high leverage point is going to be very large or very small x value. Okay, whatever point you're adding here, very large or very small, those are high leverage. Okay, influential. Influential mean if we remove the point, big change will happen. Big change. Too slow. To your y-intercept and to your r, your correlation. Okay. So your learning target number 1 here. Remember we have horizontal outlier. They tilt the line. We have the vertical outlier. These guys shift the line. Just up and down. just a reminder, learning target number 2 here. To get your least square regression line, the formula is here. The line that we have been, using technology to get. The formula for your least square regression line, which is the y hat equal to a plus bx. To get this line, you're gonna try to get your b. Your b will be the standard deviation of, your b will be your correlation, which is r, multiply with your standard deviation of y over the standard deviation of x. And we can easily find these using calculator as long as you get all y and all x, basically 2 set of data, right? And then your a will be just the mean of y, subtract b multiplied with the mean of x, okay? So after you get your b, you can use this to get your a, and then you will be able to get your least square regression line. All right, so go ahead and work on check your understanding after you're done with the notes right here. I have already posted the answer for this one. So if you struggle with this, please check your Canvas. Okay, check your Canvas for the key. I will post that for you. Now down here, we need to go over this exercise right here too. Okay, this one is going to be quick. I know there's a lot of parts, but it's going to be a quick one. Okay. So we have, can you predict Monster Energy stock value? So over here, they give us a regression line, right? This line right here. We have the equation that they give us, and we also have the R square right here, which is your coefficient of relation, right? How well is your data? How well is this little line approximate your data, right? This line, how well it is. So over here, to interpret your R square, we're going to use this little context plus the context and the numbers that we got over here. So remember the number in front of your x here, this number is your x is the year after 2000, right? And then your y, what is it predicting? It's predicting the stock price, okay? X and y. So to interpret the R squared, this is how you're gonna do. You know that it's gonna be 0.943. This line is pretty good, right? Very close to 1. The higher it is, the better your line is. So it's 94.3%. So we can say that 94.3% of the variation in stock price, basically in Y, stock price, can be explained by the linear relationship, right, with X equal to year after 2000. Okay, so you have 2 parts here, but if you were to replace stock price and basically changing the context in here, all you change with whatever they give you, right? What is Y, what is X, and what is your R square? So you can use the sentence here to interpret the R square in any context, okay? Now it's saying right here, we have to write out the equation of the regression line. Be sure to include context for the variable. Again, your y here is the stock price, and your x here is the year after 2000. So if I were to write the equation, do not write y hat and x there because they want it to be in context, right? So we're going to write stock price with a little hat there, like my y hat, will equal to negative 20.5958 plus 2.793a parentheses, and the x there was year after 2000. So years after 2000. Okay. This one's saying use the linear model to predict the stock price for 2014. Show your work. Now remember, year after 2000, and it's 2014. So basically, your x here is what? 14, right? Does it say year after 2000? So 2014, there's 14 years after 2000, right? So to predict to get the stock price in here, all we got to do is to plug in 14 into x and do the little calculation into your calculator and get the stock price. So what we do is stock price, put a little hat, we write this, A plus 2.793a. And the year after 2000, it was 14 years, right? 2014, that is 14 years after the 2000. So the answer right here, if you do that in your calculator, is going to be 18.52. So the stock price for Monster Energy stock value is going to be $18.52, right? Dollars in dollars. Okay, down here. Oh, down here. Is I find the residual for your stock price prediction for 2014. Show your work. So find the residual. Over here, if you were to look, 2014, for your table, you have 13.39. That's the actual, right? The model that you have for the predictions for 2014, predicting 18.52. The residual here, you will take the actual, subtract the predictions. Okay. So residual. Okay. Will always be the actual, subtract the prediction. So the actual that we got was 13.39. And we want to subtract that with 18.52. So this will come out to be negative, right? Negative 5.13. So my residual there is going to be negative 5.13. Okay. Now down here on number 5, say explain why the residual plot indicate that the linear model is not appropriate for this data. If you recall from the last class, to be considered a good model, your dot have to be all spread out, right? This one is look like it has a little parent. It's look like a parabola here, right? It's go down a little and then it's go up. So it's have a parent here, okay? So a parent here. Look like a parabola, right? We don't want that. If it were to be a good one, all these points has to be spread out both up and down of the line here, okay? So we can say that the residual plot has a clear curve pattern here. So always, if you were to look at your R here, right? Remember your R squared was 0.94943. If you were to take the square root of this to get back to your R, which is your correlation, it will be 0.971, right? But looking at your R is not going to be enough, okay? Look at your R is not going to be enough, all right? You have to look at also the residual plot to determine if linear model is a good fit for this kind of data, okay? So we can say right here, remember this. So remember that looking at the R is not enough to determine linearity. Okay. We must look at residual plot. Okay. So we have to look at this. You can graph this from your calculator. If you don't remember, please check your Canvas for the videos that went over how to plug in your data, and then also how to get your residual plot, and then every other good stuff like your R and R squared and everything. Okay, please check that out on your Canvas. Okay. Okay. Let's go here to number 6. So for number 6 here, because the data doesn't look so good, right? It doesn't look so good, and we are concluding that okay, this line right here is not a good fit. This equation is not a good fit to predicting stock, right? Because stock, these data doesn't follow linear. That's the equation not good. Okay. So over here, I mentioned that you can transform your data to have a better model, right? To have a better model here. So to fill in here, you're gonna just take the log of the stock price. So stock price is right here. If you take the log of that, you get this number. So I'm gonna go ahead and fill in the one that is in blank, but you can go ahead and do that on your own. So just take the log of 2.64 from the calculator. So it's gonna go to 0.4216 here, and down here this one, take the log of 13.39, and you will get 1.1267. Okay, so we have though again, your y will still be now it's going to be what? The log of the stock price, right? Because we transform our data, and if we were to graph this, right? The y will now be these number, which is the log price, the log of stock price. Your x will still be your years after 2000. If we were to interpret the r square again, then we're going to have, this is our new r right now, our new r square, 0.953. So we can say same thing, just like number 1, 95.3% of the variation in y, right? Y now is log of stock price. Can be explained by the linear relationship with x equal to the years after 2000. Okay. As I write the equation for the linear regression line, be sure to include context for the variable. Same thing, just like number 2. Now it's just what? The log of stock price with that little half because it's y half equal to, that is your equation right there, negative 0.1533 plus 0.0871, and your x is going to be years after 2000. Okay. For your we go down here. For your number 9, we asked to use the linear model to predict the stock price for 2014. Again, same thing here. To get the log of stock price, right? This is log of stock price. Just replacing the year after 2000, which is 14, right? Negative 0.1533 plus 0.0871 multiplied with 14 here. Okay. This will give you 1.0661. Okay. Now remember, this is not the actual stock price. This was log stock price. So to get the actual stock price, you will have to do the inverse of log. So you have to do exponent, right? So I'm going to do the opposite of log. Now, if it's just log, then you know that it's log base 10, okay? So if I were just to take the 10 and raise to the log here, it will disappear. So over here, I'm going to do the same thing. I'm going to do 10 and raise to the power of 1.0661, right? So then your stock price, if you were to do that, the stock price will actually be 10 to the power of 1.0661. You're going to get $11.64. Okay, $11.64 here. Again, same thing. If I were to look at what does the residual plot indicate about the linear model here for the transform data. So the plot is right here. Now it's looked like what? All the dot was kind of spread out. There's no really a pattern here, right? It's not a curve anywhere. It was up and down everywhere. So we can say that there's no clear pattern here. So the linear model is appropriate here. Okay, we can use this one, right? Okay, 11 is say on page 1 that we have a linear model of X year after 2001 stock price. Now page 2, which is the one that we just done right now, we have the X is the year after 2000, but now the Y is going to be this transform data when you take the log of all your Y. Okay, the log of all the stock price. It's asking which model will make a better predictions. So we're going to look at what? The R squared, right? See which one better one, right? R here is 0.953, right? What about the R over here? 0.943, right? The better one will be the one with a higher R squared, isn't it? And also the residual plot right here, right? We know that this one had a pattern. So which means that yes, is a model, it have a good R square, but it's not appropriate to use, right? Because of the residual plot here. It has a pattern, okay? We don't want that. This one qualify on both, right? You can see that there's some kind of pattern here, but overall, there's none, right? It's not. It doesn't look like a curve. It doesn't look like it's forming like a shape, right? So we can answer right here. So we're gonna say page 2 is the one, right? Page 2 is the one because the R square value is closer to 1, which is, we know that we have for page 2, the R square was 953, which is greater than 0.943, right? It's a better R-square. And then it's also the residual plot has less pattern and more randomness, right? We want randomness in our residual plot. Okay. All right. We're almost done here. So let's go ahead and do our quick note here. Just a recap on what we just learned on this one. So we learned learning target number 1. We learned how to transform our data. Transform. So there's a couple ways you can do. The most common one is to take the log of your data. Sometimes you can even do exponential to our data transformation. Okay, but the most common one that people do was to take the log, okay, of all your y value. So there's a couple things that you can do. Original data, and then you also have over here your transform data. Okay, if it's linear, you grab your x versus your y, just plain x and y, right? If you were to do the exponential, you grab, which is what we did over here, that's exponential. You grab your x versus your log y. The power, this is when you're gonna graph your log of x versus your log of y. Okay, you're gonna do both of them, log x and log y. Okay. Learning target number 2. We also make prediction by plugging in x and then we solve for y, right? Get y. Okay, so for example, earlier when we solving for y with the log, we have the log of y, frozen a little. We have the log of y equal to a plus bx, right? A number and then plus, that is your y-intercept, right? Plus your b, which is your slope, and then your x is your data point. If it were to be just log, you know, log is just base 10, so that's why you're going to do base 10 on both of these guys. Okay, log base 10. If you have the ln of y, or the natural log, I would say, equal to a plus bx, then to get your y, the actual y, you would have to take the e, the exponential, right? E on both to cancel it out so that you can get y. If you have y squared equal to a plus bx, then to get y, we'll have to take the square root of that. Okay, we'll take the square root. Yeah. We're going to do some more practice later on, but here are some practice for check your understanding. Down here, I do want to point out, sometimes I will give you a technology looking table. So basically this number right here, the very first one, the coefficient here, the constant right here, this is your slope. This is A. Okay. And number down here, the 2.2, that is your B. I'm sorry, this is your y-intercept, and B is your slope. Okay, because your line was in the form of y hat equal to a plus bx, right? Where a was the slope, where a is the y-intercept, y-intercept, and then your b was the slope. Okay. All right. That is all I have for you guys. Then you can go ahead and complete your check your understanding, both of them, for extra practice. If you still have question about this one, I'll see you guys back next class and we can talk about this more. Okay. But overall, this is all I have. And thank you so much for watching. Okay. Recording.